Good afternoon, everyone, and thanks again to all the organizers for this great conference and workshop. I'm very pleased to be here this afternoon. So I'll be talking about restitution curve splitting as a mechanism for the bifurcation to alternans. If I can get this to work. Okay. So we've already heard a bit about alternans, but I'll go through some of this background again. So alternans is basically a beat-to-beat alternation occurring at the cellular level, but it's also reflected at more macroscopically in the ECG and the T wave, and sometimes also in other components. So you can see, does this have a pointer? There it is. So you can see alternations just here, just in the sort of the gross morphology here. You have a somewhat smaller T wave and then a larger one, and this alternates. So, and the reason why we're interested in alternans is because it does often precede more dangerous arrhythmias like ventricular fibrillation. And here you can see it degenerating into that rhythm. So again, as I was saying, alternans does appear at the cellular level as this beat-to-beat alternation, so a long action potential followed by a short, and on and on. So this is a recording from a Purkinje fiber, a microelectrode recording. So you can see, in this case, the CL, the cycle length, is fixed. And you have a long action potential followed by a short, followed by a long, followed by a short. And this was explained a bit before. I just want to remind of terminology. So APD is standing for action potential duration, and DI for diastolic interval. And so both the duration of the action potential and also the amplitude may alternate. So when you plot action potential duration as a function of the cycle length or period, you see this period doubling bifurcation. So at long cycle lengths, you have a single value of the action potential duration, and as you pace faster, then you get a bifurcation, and there are alternating long and short values. And at very short cycle lengths, then the short action potential can no longer be sustained, and you end up with a longer one and a non-response every other beat. So every other beat gets blocked. So we saw some of this earlier in the morning, but if you plot APD as a function of the preceding DI, this gives the restitution curve, which is at least to some extent a first approximation of some of the macroscopic dynamics of the system. And so again, defining the action potential duration and the preceding diastolic interval. If you stimulate earlier and earlier, you get shorter and shorter action potentials that you can then plot as a function over here. And you can use linear stability analysis to determine that indeed the slope of this curve being 1 is the condition that gives you this bifurcation. So for slopes greater than 1, this simple one-dimensional map model will give you of just plotting, just considering action potential duration as exclusively a function of the preceding diastolic interval. That will predict that there's alternans when the slope of this restitution relation is greater than 1. So I'm going to show you how this works a little bit, but using this cobwebbing technique that you may have seen for maps like the logistic map. So actually, I think I need to be over here for this one. So this is a Java applet that should be here in a second. OK. So on the top of this, I'm plotting the action potential duration as a function of the diastolic interval. So this is the restitution curve. On the bottom, it's going to be action potential duration again, but this time as a function of period. So here's where you'll see the bifurcation plot. And on the top will be this sort of cobweb. So in this case, you're cobwebbing between the restitution function and this line of slope -1, which is the line that defines the fixed cycle length at which you're pacing, which is just the sum of the action potential duration and diastolic intervals on these two axes. So you get a line of slope -1. So as you decrease this period, you can see that you're moving along in this sort of flat portion of the restitution curve, and you're getting this single valued response. And as you start to get to this more sloped region, it's really a small region to get there. But you can see at this point that you're within the bifurcation. So you're alternating between these long and short action potentials on the restitution curve. And you can see indeed for this fixed cycle length, there are 2 different values of action potential duration. I'm going to make some comments on the following slide about what these sort of boxes. So this is what I'll be referring to. So this is just the box that's sort of when you connect the long and short action potential durations on the restitution curve with this line defining the cycle length. Okay. Well, this is a little. I think that was an extra slide. Sorry. So in models and in one-dimensional maps, like the one I just showed before, the alternans is characterized by these boxes here, and they're going to be nested during alternans, which sort of makes sense because you need to have long and short cycle lengths during alternans, and from the bifurcation point, there's really no option other than to have values that are longer and shorter. And as you move through the bifurcation in these models, these boxes sort of expand. So these boxes are nested. And the reason why that's important, and it's also a very large magnitude, and that's important because it turns out that that's not really what you see experimentally. In experiments, these boxes basically sort of slide along the curve. So they may change in magnitude a bit, but basically they're kind of sliding down the curve. They're not concentric, they're not nested anymore. So, and actually if you look at as a function of cycle length in this case, the magnitude of this alternans is fairly small. And it kind of grows a little bit initially, but it stabilizes pretty quickly. It's kind of more linear growth. Whereas this is a very, very rapid expansion of alternans. When you hit alternans, you know it in these models. And it's a little bit more subtle in experiments. It's still noticeable, but it's not nearly as dramatic. So as a way to explain this, we would posit that basically these sliding boxes are indicative of the fact that the restitution curve actually splits into two curves for this region. And in that case, these DI-APD pairs will come one from each branch. There's a long branch of the restitution relation, and there's a short branch. So it's not really a single valued function. And it turns out experimentally that this is the case. And actually, I think people have observed this before that we've talked to, but they thought it was an artifact and averaged it away. So the long and short beats sort of would cancel each other out, and you get a nice smooth average in between. But if you separately average long and short alternating beats, then you do in fact see this splitting of the restitution curve. So in this case, these are the boxes that we get here that are connected, and you can see they're sort of sliding down the curve. And again, this is looking as a function of cycle length. So these are just the values for a given cycle length, but these values slide down because the values are on these two branches, the red and the blue branches of the restitution curve. So we've done a lot of experiments with this, and I don't have time to show you too much data. So this is just some representative. The previous example was a Purkinje fiber from a canine. This is epicardial and endocardial muscle. And especially for the muscle cells, it's quite sensitive to temperature. So the splitting that you get is greatly increased. Although it's present at room temperature, I mean at physiological temperature, it increases as you move toward room temperature. So you can see it as you get cooler, so the temperature's higher here and lower here, these regions of the splitting. And again, this is as a function of diastolic interval, not cycle length. So this isn't the bifurcation we're looking at, but indeed splitting into two of the restitution curve. But you can see that it becomes quite dramatic at low temperatures, but it is present as well over a smaller region at high temperatures as well. So again, basically you have the two branches, and for the 2 points that are involved for a given cycle length, the only restriction on the slope of any kind is that the slope connecting these 2 points for a given cycle length needs to be 1. But the branches themselves can have any slope. So in this case, you can see this blue branch is pretty steep, and this red one is even steeper. Whereas over here, you can see these branches are much less steep and much less than 1. So all of these green lines show lines of slope 1 for comparison. So this is really the only one where it's a very steep slope. And this seems to be more characteristic of Purkinje. The muscle cells, so these are examples from epi and endo, are more likely to be flat. And also, this long branch, the long APD branch, is always shown in red in this case. And usually, as you would probably expect, the long APD branch is above the short APD branch. But it doesn't actually have to be that way. So this is an example where, in some sense, the short branch is sort of above the long branch. But because of the steep slope, it's able to have, it's still able to split in this way. So we have found if we change the environment of these experiments by reducing extracellular calcium, we get rid of the splitting. It also eliminates alternans, but it does seem to indicate that calcium is likely to be involved. And indeed, we've done some work using a two-dimensional map model that basically includes a calcium concentration as well. So the APD is no longer a function solely of the preceding diastolic interval, but also of the calcium concentration as well. And I don't have time to go into details here, but essentially you can see that the experimental data that's in the solid line is well matched, or in the dots is well matched by the two-dimensional map. So both for the cycle length plot and for the splitting in this diastolic interval. And this is for Purkinje as well. We also looked at this in some mathematical models. And there are several different models that do show splitting in the restitution curve when you look at it closely. So just showing a couple of examples here. So these are both canine models. So this is the Fox-Makar-Gilmore model, and this is the Hunt-Rudy model. So in both cases, they show splitting. So again, this is as a function of cycle length, showing the bifurcation on the top, and action potential duration as a function of diastolic interval on the bottom. So this is, in fact, a split restitution curve. And this one, it looks like it doesn't really split, but if you zoom in, it actually does. So it's a small amount of splitting, but it's there. So, and in this case, again, you can have slopes that are steep or not as steep. So we've done some experiments in the models trying to look for what controls this splitting of the restitution curve. And in the Fox et al. Model, we found that by altering some of the intracellular calcium dynamics, specifically in the uptake current by changing this exponent, we can actually enhance the splitting. So on the bottom, we're looking at the exponential duration on the left as a function of cycle length and as the right as a function of diastolic interval. And this rainbow of colors, as you increase, everything doesn't actually change this much, it just everything overlaps. So this is sort of sorted out so that you can see each curve individually. But you can see that the splitting of the curves increases as you decrease this exponent. And what a nice surprise in this case is that when you do this particular intervention, because there are lots of ways to get rid of alternans splitting, but restitution curve splitting, but it also gets rid of alternans. But in this case, you can enhance the splitting while at the same time largely preserving the magnitude of the alternans. So actually the original value, which is at the bottom, is kind of the smallest magnitude of alternans. But a lot of these others are very, very close in magnitude. But the splitting, you can see, increases very straightforwardly from these low value, from the higher value of the exponent to the lower. So just to summarize, this restitution curve splitting does occur. We found it both in normal Purkinje fiber cells and ventricular tissue as well. And the slope of the branches of these restitution curves no longer have any type of restriction in terms of the slope function, which has also been known because there are a lot of other effects that also, electrotonic and memory effects, that also can alter this slope greater than one criterion. But this is yet another way in which the slope is not necessarily the criterion, the sole criterion of interest. And we've been able to see the splitting in a two-dimensional map as well as in more physiologically detailed models. And I'd just like to acknowledge Flavio Fenton, who's a co-author on this, as well as Robert Gilmore, and funding from NSF and NIH. So thank you.
Thank you very much. Yes.
From our experimental data, I know that induction of AV-NRT is very difficult process, and usually window of vulnerability in which you can induce AV nodal reentrant tachycardia is really sometimes just a few milliseconds. But I've never given any thoughts in terms of APD restitution in the AV node or slow and fast pathway. And I was just wondering, from your perspective, do you know any data or any theory relating to structures like AV node in terms of APD restitution and splitting of your?
Okay. So I think the question basically then is there any data that I'm aware of anyway on the possibility of restitution curve splitting in AV nodal tissue? At this point, we haven't looked at that, and I'm not really aware of anyone else who's been looking at restitution curve splitting in particular. So it would definitely be interesting to look at that and see if the window of vulnerability is different in that case.